So I hope okay, so welcome back to the second part. Okay, now what we want to do now is actually talk about supervised machine learning. Do I need this? No, I don't need this. Okay. Okay, so let's go to supervised learning. Okay, once again, you guys remember that I show you linear regression as a supervised learning, right? And again, and this is in your exam, right? So recall the three modes of machine learning, right? Unsupervised, supervised, and reinforcement. Okay. This was actually the baby question that I gave for your exam, right? Just for you to feel confident. Okay. Now we did a little bit unsupervised learning, clustering. Okay. I make a point that regression equation, okay, can be thought of as a ready-made formula for creating a very simple form of supervised learning. One that can learn linear. That's, remember the difference between linear and affine relationship. X and Y, where X can be a vector, Y is scalar. Okay? Right? So I make a point, okay? So what's the point? The point is that every data point is a pair of X and Y, i.e. X points to Y. That's how you want to think of it. Okay? And then you have a function, you have a function f of x given some kind of parameter b. Okay, e.g. b0 plus b1 x1 plus b2 x2. Okay, right? And then you want to fiddle with b until f of x given b, all of this are close to y, right? Fiddle, okay? The point about linear regression is that because of the function is simple and you use calculus, this has a formula for you, okay? So the difference here, key difference with regression, let's say simple regression, you have what? Just one chart. Just have you have a formula. So one shot. With general machine learning supervised learning, you start with random parameter. Okay. And move it down the valley. Right? We talked about this, right? This is 2 weeks ago, but I hope you haven't. In fact, if you open the note from last time, it looks a little bit like this as well. You move it down the error valley to get as low as possible. Okay, that's it. That's what you want to do. Okay, that's what you want to do. Okay, now let's go to supervised learning. So what supervised learning? So let me just run this number real quick. So this is male female height, right? We did this before. Let's plot this thing. Okay, so obviously you can fit this line. We did that, right? Now this part here is prepare your data set. Okay, so we have X and Y. Okay, you have list. There's a bird. Huh? Okay. Now, simple as that. You turn this into now this is mathematics way of doing things, or you can do this as well. Okay, now this is basically it. This is all you need to know. It's you know, normally this step can be a little bit painful, but the first thing in mathematics is simple is this. You have now I'm assuming that X is right now it's just a value, right? But it could be something like well let me do this. Okay. Let me do X1 1. This is the input, and X1 2. Okay, now that's better. That's a bit more generalized. Okay, so now you have this. Okay, now let me make it larger. Can you guys see this? Okay. Now imagine this. This is assume. Suppose you have n data point. Okay. That n data point in this case, okay, you can think of this in your head. X11, X12 is the first data point. This is dimension 1, this is dimension 2. Okay, so you can think of it as two-dimensional problem. Okay, now this could be whatever, but I'm just going to stick to 2 dimension. So this is going to go to xn1, xn2 to yn. Okay, so you can see that, right? So think of it as an Excel. Okay. Sorry, as a table. Okay, so this is I is the row. The first row is the first data point. The n row is a n data point. Okay. What you want to do is you want to put an arrow in between. You want to put an arrow between. So you can do this. Turn this into, I want to turn this into an arrow. So it has to be an arrow here like this. Okay. But if I did this, what's gonna be the interpretation? It's gonna be x11 and x12 point to that, right? So I have to make this into something like that. List of input pointing to output. Okay. This is, so now you have a list of inputs and output. Now, in fact, now this is very important. I load this, okay, because I have intention to use the first two as your variable, as your explanatory or input variable, right? But in real life, you're not going to see that. You're going to see something like height 1, weight 1, and what's the third dimension of a person? Waist 1. Okay. There's no designation of what's X, what's Y. You have to make the decision. What's your problem? Your problem is to predict height from weight and waist, or predict weight from height and waist, or predict waist from height and weight. So you have to make the decision which one is your Y. Okay. But let's say you make up your mind which one is your Y. Okay. Then you see you get something like this. Okay. So you have to turn list of inputs and outputs into list of input pointing to output. Okay, or list or into, you can do this as well. Okay. This is called list of inputs pointing to list of output. Okay. Now, mathematically, I can do both. Okay, it depends on how convenient. I tend to like the second thing. Okay. So this is a list of input pointing to output. This is list of input and list of output, and we have list of input pointing to list of output. Okay, so let's do that. So now I have, well, in this case, because I only have height and weight. Let's say you want to predict weight from height or height from weight, doesn't matter. Okay. Now in this case, let's say I want to, let's say my IO. Let me show you this, okay? Let me show you this. If I do this, what's that? What's that? That's list of input pointing to list of output. Okay, this is list of output. Okay. So input is height and output is weight. Is that right? Height and weight. Height and weight. Okay. Why does it look? Oh, okay. Sorry. That's okay. That's okay. This is American. So height is in inches. Okay. I thought this is kilogram. Yeah. This is height in inches, and this is weight in pounds. So that makes sense. Height to weight. Height to weight. Okay. Now there's a function that sort of like instead of doing this, it goes one by one. That's called threading. It's the same. So if I put this under thread. Okay, so in other words, you have two things, and I just thread the first pair together. See this? Can you guys see that? Okay. The first one is list of height, point to list of weight. Second one is list of height to weight, height to weight, height to weight, height to weight, height to weight. Okay. You can use both. You can use both format. I tend to like this format better. Okay, I tend to like this format better. Because especially if your input is a vector, then it's clear. Okay, that's what. But anyway, you don't need to do it. But okay, so I make this input. So that's my data. Now I call this function called predict. Okay, I call function called predict. Now technically, prediction is a wrapper, meaning it's generic for all methods. So in here, I can say something like methods to neural network. Okay, I can do this. Okay. Now, when it does this, it's going to call. We don't know about neural network yet, so let's not use that. You know linear regression. Okay. Right. So this is to build a linear regression. Now, because Mathematica knows that in most cases, there are basic methods you want to play with. Linear regression, multi-layer perceptron, support vector machine, random forest, gradient boosting, with some basic set of parameters. You can do this automatic. Okay? And it's just going to try a few of them. And then based on some criteria, choose the one that is simplest but explains the data the best. Now, because it's senseless to do this, so you can just omit it. So it's going to pick the best model in terms of performance. If the performance is similar, then it choose the one that's simplest. Now, because the data set is so simple, do you think it's going to go to like a neural network, random forest, gradient boosted tree, Gaussian process is going to do that? No, it's going to pick simple things like linear regression because this is simple. So without specifying, I asked it to build a model, and sure enough, it is a linear regression. Okay, it's a linear regression. Now you can use this as a function. This becomes a function. So if I want to predict the weight of someone who is 61.2 inches, okay, that should give you some number between like 120 pounds or something. See that? And that's simple because the data set is so nicely linear. You can see that, yeah, 61 goes to 123, 62 to 126. So you would imagine that 61.5 is sort of like halfway between this and that. Okay, not quite. It's not 124.5, but it's close, right? Because it's making some kind of interpolation. That's what it is. Okay. Now, here's the point. And this is something that I don't think there's an equivalent in Python yet. I don't think. Okay. So use predict function, right? IO data, set, say whatever you like, whatever, okay, something like that. Okay, so this is your IO data. Assume IO data is list of inputs pointing to output or list of inputs pointing to list of output. Okay. Same thing. Okay. Then you just use this one. To create your model. My model. Okay. Note, leaving method unspecified will let Mathematica try a few basic ones. Okay. So what are the basic ones? Nearest neighbor. Multi-layer. I'm going to write this down for now. Okay. Nearest neighbor, linear regression, multi-layer perceptron, SVM, support vector machine, gradient XG boost, gradient boosting, random forest, distribution tree, Gaussian process, something. Okay, so these are the basic one that sort of like built in. Okay, you don't have to build anything fancy. They're more built-in fancy, but you have to know them by more specific name. Okay. Now, what's nice about this is that this is an object. Okay. This is a function. You can use it later. Then use predict y predict is equal to my model new x new one x2. Yeah. What I mean is that once you have this, you can put in anything. Okay. Now, with Python, you have to write an evaluation loop. In other words, yeah, it's giving you the best model. It's giving you the best model, but that's like working, you know, sort of like very, very ignorantly. Okay, you just build something, you don't even know how well it's doing. Right? What you want to do is understand how well it's doing. So in linear regression, if you go to, let's say, go to Google, okay, criteria for assessing a regression model. Okay? So there's all this, right? R square, root mean square error, blah blah blah, right? Okay. Now you can write that, you can call a function like in Python, but in this case, what's so nice is Mathematica can actually evaluate all of this ahead of time, and we call this predictor measurement. Okay. So this is measuring the performance. So I'm going to give the thing that I created and the data. Now this is a data. Happens to be the same data that I used it. Okay, but it could be a new data. It could be a test set. Okay, but right now I haven't got a test set because it's so small. I'm just going to use the same one. So I create this thing. So this thing say it's a linear regression it has all this information, standard deviation, baseline, R square, mean cost, entropy, single evaluate, batch evaluate. It has more than this, but this is the basic one. Okay. In fact, let's look at the properties. Okay. Now, I think not people too, but in scikit-learn, like in Python, you actually have to call individual evaluation function. This in Mathematica, because it assumes, you know, you're a data scientist, you'd be interested in knowing what the performance metrics are, right? So it evaluates all this ahead of time for you, okay? Mean square, whatever, perplexity, all some of this I don't even use, okay? The main one I use would be something like residual plot, R square, well, it produces histogram for you. It lists certain example, most certain example, mean probably, it gives you more than you need, okay? It gives you more than you need. But let's say I'm going to care about basic report, residual plot, and this. So this is it. The basic report, well, that basic report is the one that you saw earlier. This is the residual plot, and this is R square. Now, right away, it tells you what does it tell you? It tells you that even though linear regression is the best model because it's simplest, it's actually a wrong model. Why is it a wrong model? Because you notice the pattern in error. It's not random noise. When you do linear regression, you assume that the residual plot here would look like a Gaussian, up and down, up and down, up and down, up and down. Some overpredict, some underpredict, some overpredict, some underpredict. But in this case, what happened? For short people are heavier than predicted. This is actual minus predicted. Short people are heavier than predicted. Tall people are heavier than predicted. Medium height people are not as heavy as predicted. And this is pounds, right? Plus minus 2-3 pounds, right? So you will see that even though it looks like a straight line, you can see, yeah, there's a slide that gets magnified. So this is something that all your project, now in your project, you will use different techniques and whatever, right? But at the end of the day, you have to produce basic information about your error. Okay, so that's why, okay, if you go back to the syllabus, okay, this thing here about performance assessment is a big deal. Where is it? Performance evaluation. Okay, performance evaluation. Okay, so that was supposed to be September 28th, but September 28th moved down to today because we actually had, I should make this a midterm exam. So let me correct that later. Okay, so this performance evaluation is the basic thing, right? You're familiar with R square? We use that a lot, yeah? Residual plot, all kind of things, okay? You can do, say, probability density histogram or residual histogram. Well, residual histogram, you would see that it's about, you know, a little bit over to 3 down to -3, okay? So that's an example. Now, let's try, well, this an example of a data set. Actually, I'm just going to add this data set for you guys to play with, just for fun, I think. There, okay. Basically, this is a website. Yeah, this is a website that I use for teaching purpose. I can't use it professionally because it gives you a very old data set, a very small data set, but it's good to play around with. Basically, if you type in something like this with the name of the company, okay, so this thing gives you a stock price. Now I happen to pick for this example Caterpillar, JP Morgan, whatever. You can pick any company you like. So so this is basically the data: date, open, high, close. Now this is what I mean by more convenient to work with data set. So let's go to this. Okay. Now, so I'm gonna show you just this. Okay. I'm gonna retrace the step. I'm going to just import Caterpillar price. Okay. So it has date, it has open, high, close, whatever. Let's see what the dimension is. Yeah. So it has 1091 row. Well, the first row is a header. So actually there's 1090 dates, and it has 13 number, right? Now, obviously, let's say I want to work with list. Okay, I found the list. I can do that, right? I can say list. I can say, well, let's look first. Data cat. Okay. So let's say I want to look at the close price. I have to remember that close is 1, 2, 3, 4, 5. So let's do that. Okay. Second row on and 5. And let's say list line plot. Oops. Okay. Right. So that's it. Okay. I have to remember that the data starts from second row and I want the fifth column. But if, okay, if I create a data set first, which, you know, same as what we did before. Now I call data set, just like before. Okay, it's gonna look like this. Now I want to say close. I'm just gonna say, well, let's list line plot data set. Sorry. Okay. Right. And again, if this is a data set, I can do certain things like I don't want to take all, I want to take just the first day, few days, blah, 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 and can do all kind of stuff. Okay. Just again, much nicer to work in data set, but you don't have to. Okay. In fact, this example was written for a class that didn't know data set. So I make something. Okay. So this is like working with data. Now, this example, I'll give it to you as well, but the only thing I want to point out, here is this. When you work with real data, okay, yeah, you want to work this, so work in the format of the data too, okay? But that's not enough, right? So maybe I should say, take it A. B. You want to partition data into frame. Okay, I'm going to use the word in sample. Now you can, sometimes you prepare the format first and then this, and sometimes you do this before that. But what are these two steps? In other words, e.g., if you had 100% of data, okay, from the 100% of data, show predictor only 80% of the data. Then show the other 20% to what? To this guy, right? To this guy, to this guy, this guy, this guy. This is very important. Okay. This will give you confidence that you are not memorizing. Now, this is a little bit hard to understand. When you learn regression, okay, when you learn regression, you have 100% data, you use 100% data. You never do this. You never do this. You take the whole data and you fit everything using linear regression. The reason you do that is precisely because linear model can't do much. It can't do much. It can only fit a linear line. So it's not going to overfit, right? It's not going to overfit. It's not going to overfit. It's going to give some error. In fact, this is where you get the error. Okay? Now, the opposite happened with advanced machine learning. You have so many parameters. Okay, and I'll talk about parameter count at a later point. It's actually able not to just fit the line, but actually it can remember every single data point. Okay, so you know that it's a very actually it's a very hard thing to explain, but a model that a neural network creates is very much similar to memory creation. Okay, when you make prediction between X and Y, it's a little bit like the last time the air feels damp and the sky looks dark, it rained. So when you see that the air is damp and the sky is dark, you predict that it rains. It's going to rain. That prediction is a little bit like memory. Okay, you think you're learning the function, but internally it's a little bit like memorization. So if you can memorize all the rainy day in your past, sometime you would overfit. You would say that, yeah, it would also rain if it was a Friday, because that happened to be Friday. Okay, but in fact, it has nothing to do with the fact that it's Friday. So the memory, the neural network, the machine learning that you're going to learn in this class is so powerful, it can memorize every single data point. So obviously, it's going to make perfect fit, but it's going to overfit. It's going to fit individual data point. So you don't want to do that. You want to hide some data set. You want to let the new, okay, fine. You want to memorize, go ahead, have at it. But you can only memorize 80% of the data. I'm going to test you on 20% of the data, right? So you really have to be able to, what's the word I'm looking for? Generalize. Overfitting and generalization are the opposite. Okay, so let me write that down. Let me write that down. This is very important. With, say, linear regression, you cannot overfit. So give 100% of data to train. With, say, I'm just going to pick one. You easily overfit. So give 80% to train NLP model. Okay. Then test. Yeah. Hit them 20% to see how well in order to see how well the NLP model. Then okay, that is the true thing. Okay, so this thing you would have to do anyway because Mathematica on this thing you have to do anyway because whether or not Mathematica or Python, you have to make sure you tell the program who's the input, who's the x, who's the y. Basically, this is separating x into x and y. Okay, otherwise it doesn't know to predict what from what. Okay, but with linear regression, you just throw the whole data set like I did just now. Okay, but with other more advanced model, you have to do the separation. So this is why there is this step in between, and I'm gonna sort of like give you a quick. Okay, so this example, okay, my model data, okay, I have some other function that make time series data. Okay. This is my shorthand for this thing. Okay. Now, this is the function called take drop. Okay, take drop means, well, let's look at the function take drop. Okay, now let's take drop is very simple, right? You take the whole data set. You take the first this many. You take this many. Okay, so if I have say 10 data set A, B, C, D, E, F, G, H, I, J. Okay, and I take the first 3, right? It's gonna take the first 3 and leave the other 7. Okay. Now, what I want is I want to take about 80%. 80%. So what I would do is 0.8 times length of this. Okay. Very nice, right? The length happened to be 10. The length happened to be 10, right? So I take 80% of the length, so that's 8. So I take the first 8, I put this, and I call this my train, my test. Okay, yeah. So now this is my train. So obviously this is not a training set because it doesn't have the error. But this is just to separate. to show you the separation. Now, obviously, if this happened to have 11, that's going to be a bit messy. Okay, why? Because 0.8 of a length is not an integer, right? So I have to do something like floor or something like that, round down. Okay, so this is a standard way of doing things. Now, in neural network, and I'll tell you why later in next class actually. Okay, instead of for next class, you would see that we actually separate yeah, I'm gonna call it training set, validation set. Yeah. Next class. Not two. Two. We may need to, okay, in some cases. Okay. Let's put that under asterisk. Okay. So now, okay, so now for I happen to have this, but basically I have a training test set and so forth, right? And I can create a predictor model, whatever. Okay. This one happened to use linear regression or whatever, predictive function, and you do the same thing, and you get same kind of report. Now, this is a little bit more realistic, to be honest. This is actually a nice data set to have linear regression because, you know, if you think of this as an outlier and you ignore it, this looks like a Gaussian noise. So it's a very nice fit. Okay, you can do this in real life. So you can play with this. This data set is surprisingly simple to predict. Okay. So I can predict, I don't know what it is. Oh, okay, I think it's the price of 3 M's. I think it was 3 M's. Okay, not cat. So this here shows you a prediction. Now, it's still using linear regression because it turns out to be very easy function to, model to predict, data set to predict. Okay. Okay. You want to ask me why, if the stock price is so easy to predict, nobody's making millions of money, like millions of whatever? I just told you that, yeah, you can predict very high accuracy. You got what? 99% accuracy. 99% accuracy. Okay? Even if with this, even if you have this, you still can't make money with stock market. Now, this is a 99% accuracy out of sample. Okay? I think. Maybe not. Yeah. Price table. There, see? So I train it with train, but I test it with test data. So it's out of sample and it's getting 99%, 98% accuracy. Okay. So predicting stock is as easy as it gets. Okay. You can get 98% accuracy. Okay. Ask me later why you still cannot make money. Okay? But I just want to show you. Now, so this here is the first step. Okay? So when y is equal to, what's the next step? What's the next step? Next step is actually not neural network. Next step is actually nonlinear regression. Okay? Nonlinear regression, I'm just going to make it very quick, okay? And you don't have to copy all normally I want you to key in everything, but now you don't, okay? Basically, instead of saying y is a linear function of x, you make an assumption about the nonlinear part. In this case, I make an assumption that it is x squared and x to the power q. So I create this data set. Okay, I create this data set. Okay, I could. Oops. Generate map. Okay, so I make this function. I just make this random function. Okay, now obviously this data is very easy to fit. Okay, because you can see that it looks like a third order, right? So you have a constant, linear, quadratic, and then you have third power. So this one is easy to fit, but you cannot fit it with linear. So instead of saying y is equal to function of x, instead of saying y is equal to b0 plus b1x, you say something like, well, x is just a function. I'm just going to call it b2 and then another function called x squared. Square, where's the square? X squared. Okay, plus b3 x to the power 3, something like that. Okay. In fact, I don't have to just raise the power. I can do this as well. Okay. This thing is now called kernel function. Okay. So back to linear regression. Y so a plus bx. How about now nonlinear? Introduce nonlinear. Y so a plus bx plus c x squared plus d log of x. Okay. X squared and log x are called non okay, kernels. Okay, kernel is an English word for nuts. You know, little nuts. So it's the essence of a fruit. Is the nut. It's the kernel. Okay, so if you chose the right kernel, you can get pretty good fit. What's wrong with this statement? What's wrong with this statement? It's circular. If you knew what the right kernel are, then you must have known what the model, the best model is. Okay. By the way, this statement, I think there was one of your classmates asked me about a project with support vector machine or something like that. Some kind of cryptographic machine learning project using SVM. This exact statement applies to support vector machine. This is also, I never use SVM. SVM can do a lot if you have the right kernel. But if you knew the right kernel, you already know the solution, right? Okay. I don't know if your friend's still with you in this class. I'm not sure it's the same class or not. Anyway, that's quite a class. But it's the same thing. Support vector machine is a linear kind of separation. But if if you have a nonlinear separation, you have to pick the right kernel. But if you do the right kernel, you wouldn't have to do it to begin with. So in reality, you just guess. Okay. So in practice, you just guess. Put in as many kernels as you can work with and hope that the regression the coefficient will drop out for nonsense. Okay. In other words, you just put in all kinds of functions here, right? And hopefully the coefficient. So if for example this thing doesn't make sense, then this coefficient will have poor significance, low statistical significance. Okay, so you can do that. So I just want to show you real quick. So obviously this is not a machine learning class. You don't need all the basic fun, but you can do all this. So you can fit. So I choose kernel. Well, obviously it's going to have the right fit because I cheated, right? I cheated. I knew what the model is. I generated it. But I want to show you just a slight variation. This data was created using x squared and x cubed. But I want to show what happened if my kernel does not. Where's my kernel? Yeah, my kernel does not have constant, right? So in other words, this thing has number 3 in it, but my kernel doesn't contain number 3. So it forces the intercept to be 0. So that's why it's not perfect fit. Now, if I put in something like 1, comma, okay, 1 is a kernel. If I put this, I get a perfect fit. I'm pretty sure. Fit kernel. Say fit kernel. Fit kernel 2 equal to this, and I add 1 to it. And let's try this guy. Why do I not have this? Okay, let's see. Perfect fit. See? So again, if you knew what the right kernel is, you get, now, if you don't know the right kernel, say, I knew that the first and the second is the one I used to generate, right? But I just do this. Okay, I chose the wrong kernel. And I fit. Yeah, it's not perfect. If you knew the right kernel, you get perfect. Okay, so this is a bit of a lesson. Okay, now I'm not going to save this, am I? Okay, I'm not going to save this. So what I want to do is, before I get to that, I get to this thing called logistic regression. Now, so supervised learning problem. I'm going to separate it into one, regression, okay, and two, classification. Again, this was also in your exam, right? So if regression, your y, target y is belong to what scale? Guys, interval ratio scale, right? And here, target y belongs to ordinal, right? Y1 equal to 1, 2, 3.5. Okay. Right? Now, you know linear regression. Okay. Now, the rest of the class, I'm going to give you something very simple. Very simple. Binary classification. Y star 1 or 0. i.e. true. Okay. So how would you do this? How would you do this? So remember that linear regression y is in minus infinity, say plus infinity, okay, in general. Yeah, there's no bound, right? But y is in here. So how do you do this? How do you know how to do y minus infinity to plus infinity, but you don't know how to do this. So here's a trick. Here's a trick. Let's say y large. Okay, y large means you very sure y. Okay, so I'm gonna change from y to, let's say, u. Okay, y u. Okay, let's call it bracket y. What should we call this? Bracket y. Okay, so let's say y large and positive. That y equal to me. Likewise, y large negative means you're very sure y is equal to 0. Okay, y is equal to 0. And so if meaning y near 0 means you not sure either way. Okay. Yeah. Now, instead of this, how about this? What if this is the first trick? Step 2. Then very sure y1 means p close to 1. Okay. Very sure y equal to 0 means probability close to 0. Now, finally, not sure either way means close to. Does that make sense? Now stare at this for a moment. This is all the logic you need to understand. Again, my class is based on understanding. Okay, the tools are already done for you. Let's say that y is very large. Okay, so in other words, if, for example, y, okay, y, okay, good guy. Yeah. And then y is some kind of rating. Okay, let's rating a good company, good product. Rating score from internet. Yeah. Now, basically, you want good or bad. Good, not good. Okay. Good product. Okay. But y is not good. So what you do is, if y value is very large, you are very sure that it's a good product. If y is very low, negative, you're pretty sure that y is a not good product. If the value is around 0, let's just make it either way. You're not sure. So I want to work with another value called p that thinks it's a probability. Okay, think of it as a probability. It's not quite a probability, but it's kind of some kind of subjective probability. Think of it as that. Okay, can we do that? Well, in that case, with that, you can make a regression model on y, then squeeze y to p. What do I mean by squeeze y to p? Means that i.e. y near large, p near 1. Okay? Y negative large, p near 0. Y near 0. P near 0.5. Okay. Now let's see if we can find that function. Okay. So let's find this function. Okay. Let's find that function. Let's go to plot x minus 100 to 100. Oops. Okay. Now this is the function y(x). Okay. Now I'm going to change. Okay. Watch. I'm going to add another function minus x. Okay. Now I'm going to get a third function. Okay. Now I'm going to add another function. Oh. Finally, I'm going to add another function. And I'm going to take away all these guys. See that? This is now, instead of saying that this is my y. Okay. So instead of x, it's now an output of a regression. Okay. And now this is my function. This function is called logistic sigmoid. Okay. Now let's go F1. Looks like this. So now instead of, let's make it less dramatic, this minus 10. Okay. So now instead of plotting this, I'm just going to say y is equal to logistic sigmoid y. Okay. So this is essentially your P. See, when y is very large, the probability in your mind that it's a good product is near 100%. When y is really negative, you get a bad rating. Probability that it's a good product is near 0. You have no confidence. But if the rating, averages out, some say plus, some say minus, and overall it balances up to 0, you're not sure either way, so you give it benefit of the doubt. So probability of being a good product is 50-50, and it's very smoothly. What is so nice about this function, this property, is that it's always increasing. Now it looks like it's flat, but if you take a magnifying glass, it's actually slightly increasing, but it's always bounded. So that function is logistic sigmoid. So if y, instead of y is equal to a plus bx, and then p is equal to 1 divided by 1 plus e exponential minus y. Okay. Now I'm gonna take my opportunity to say b0 plus b1 x1. So now it doesn't have to be just a scalar, right? b2 x2, right? So this is my equation. What p is equal to and this is called linear regression equation. Okay. So this likewise plus error is logistic. That's it. So this is why logistic regression is everywhere, because it's as easy as regression, but it turns your regression problem into a binary classification. Okay, so there it is. So now you know how to turn regression. How about what if you have more than one class? More than binary. Okay, so more than one class, i.e. cat versus dog versus rabbit. Well, you just have 3 logistic, right? And what? Compare which one is highest. So example, let's say P, let's say e.g. P cat is equal to 0.98, P dog is equal to 0.6, and P rabbit is equal to 0.2. What is your conclusion? Your conclusion, what's your conclusion? Your conclusion is most likely cat. Okay? It's most likely a cat. Now, okay? If you think about it, what we do today, we have linear regression into non-linear regression. Okay? And you have linear regression into what? Logistic regression. Okay? What can you do if you could do non-linear logistic regression? That of this class. Huh? So yes, if you were, very nonchalant, very careless, you just want to get some result, you can actually go to a YouTube video and just, look up tutorial on how to use, Python, Mathematica function, and just do what I show you, this fit, and not know anything about what you did. Okay, that's also doable. Okay, I don't believe in that. I believe that you need to know what it works under the hood. And without you knowing it, today, I've actually given you an essence of what a neural network is. But I haven't told you, I haven't used a single word of neural network. But believe me, you have learned a lot about it already without knowing. Because I kind of snuck a lot of things in here. Okay? Under like word like squeezing function or nonlinear regression. Okay, but it's all in there. It's all in there. Okay, so this is your note. This is your class note. Now your homework. Okay, your homework, and I will give it an assignment. You will not be graded. Is I will give you a couple of videos to go and watch, basically. Okay, and right now I'm actually looking at your project, taking a look at your project proposal. So this here today, okay, part 1, you have the basic tool that will be needed for your thingy, for your projects. And then part 2, you start to learn about this. I put this in a bracket because you don't know that it's a neural network yet, but next week I will give you the sort of like the review, the spoiler. Why is it that essence of what you've been doing here is really what's inside a neural network, but obviously a lot more complicated. Okay, so this week you understand 2 things from linear regression, right? Linear regression is from the last year. You understand that linear regression, instead of thinking of x, you think of x as a kernel. You can then add x squared, x cubed, log x, whatever, and make it a non-linear regression. You think of linear regression, and you can squeeze the output into a function that gives you some kind of probability of something. So that helps you to do the classification. So this is a nonlinear regression, solve regression problem. This one, the name is regression, but solves classification. Okay. What would you do? In fact, it would do both regression and classification. Okay. So you take this bit, add that bit, a whole bunch of other things, and then you can do, becomes known as universal approximation theorem. Which can do just about anything. Proof by okay. So this is really powerful. It's not only saying that this thing that we are going to learn you are going to learn, not only is it going to be able to solve regression and classification problem, it's going to be able to do it in nonlinear way. There is a watertight mathematical proof, which I will not go into because it's a master course and it takes actually a whole 3 hours when I took it anyway. There's mathematically proven that it can do just about anything. It can do just about anything. It's that powerful. Okay, and well, obviously you know that because the world is run by AI now. But think about it. You know now because you see the result. But universal approximation theorem came out in the 70s before the machine were ready. So this was known that in theory, computer would be able to recognize cats from dogs and do deep fake or whatever, something like that. But back then, it was just imagination because the computer didn't have the power and the algorithm technique to do. But now, you might think it's trivial. Yeah, obviously, AI can do anything. I can see it. But in my generation, it was not trivial. It was a big deal to prove ahead of time using mathematics that AI-like machine, like neural network, can do anything. So this is actually a big deal, very big deal. But you guys take for granted because you live in a world that a lot of things are done for you guys. Okay, so let me save this. Now, other things here, maybe you want to, I'll give you this. I'll give you this to play with. Again, you need to run this header file because some of the shorthand that I use uses what's called the header file. So I gave you the this file, pn header or something like that. Pn header. Yeah. So you use this. Okay, and let me add that. Let me just go ahead and add that to your class. Today we use this guy called supervised learning. Well, I would actually give you the other note as well, but you can look ahead of time. So this one I'm going to be covering next class. Okay. Okay. So with that, let me make sure not to save anything because I don't want to overwrite stuff. Okay. So this one, okay, logistics sigmoid. It's a very useful function to learn, right? So that's that. Logistics sigmoid F1.
อาจารย์คะ
ครับผม
Can I have untitled 3 file as well because I couldn't catch up some part of OWID COVID.
Oh, this one. Okay. It's a little bit messy. I'll give it to you though. Okay. It's a bit messy if you don't mind. Okay, I haven't cleaned.
I don't mind.
You don't mind? Okay, you don't mind. Okay. Okay, I'll tell you what. I'll give. I think it. Okay, I'll make a nicer one for you. Okay, I'll send it to you. Okay.
Thank you.
Because I think I copied from the header file. I think I copied from somewhere else. And if you use it, you want me to limit it. Okay, I'll give you a simple one.
Okay.
So I'll call it bits and pieces as usual. Okay, I'll call it bits and pieces. So that one doesn't have the machine learning or anything yet, but it teaches you how to do the group by and stuff, which is something powerful. Again, it's something that Excel cannot do because you can't do a lot. You can do a little bit of query nowadays in Excel. There's like a pivot function and all that stuff, but it's really clumsy. So this group by, this selection, this thing is a lot more useful. Okay, and okay,ครับ. So let me send that. Okay, I'll send that to you within 5 minutes. Okay, okay,ครับ. Okay, anything else, guys?
May I ask how much does a midterm exam contribute to the final grade?
Not much. Maybe 5-10%. Again, I wanted to test the exam plus. You have to agree it was a very easy exam. Okay, maybe I give you 10% just to be nice. But it's really easy, right? The main thing is your project. Now, in your project, okay, let me just spend 5 minutes on talking about your project. Okay. So let me write a little bit of notes. Okay, I can use the old note. this guy. Part 3, bits about your course and your project. Okay. Midterm is about maybe 10%. Sounds right? What do you guys think? Because I expect you to get all correct. Okay. Project is big. Okay. So in your project, okay. So project obviously number 1. Okay. And this sounds a little bit mean, but it's not. You have to find your data. Okay. Now you can use data example from Mathematica or find it elsewhere, but you should find your own data. Okay. So that should be most so everyone speak. Yeah. Your data. Number 2. Okay. Number 2. Demonstrate basic data analytics skills. First of all, what does it mean? Obviously, visualization. What I call, preparation to. So preparation, all kinds of stuff, right? For example, working with the data set and so forth. Okay, visualization. Basic statistical description. All right, you have to know something. All right, preparation, especially data set object for tabular. Okay. So that's what you need to do. Now, the fun part, okay, the fun part is obviously as a project, you have to have some kind of, as a project, you need to have some kind of clear objective. Okay. Sort of like business objective. I don't mean business as in making money. Business as in what you want to do. What's the activity? Okay, what you want to do. I call it business objective. Then talk about formal. Yeah. Yeah. Or formulation. Supervise learning, whatever, clustering. Okay. Data mining, okay, formulation. So I would call this sort of like yeah, I use the word business. Okay, I don't mean business as in business, but I mean just kind of like work. Okay, this is a formulation. Okay, I want to say predict Y given X or cluster Y and so forth. Show thought into the methodology. Okay, why this, that technique. Okay. actual data experiment or model development yeah, this is the hard part. 6, because you are Basai student and not just engineering student, you have to think of some kind of wrapping, packaging, demonstrating, okay, prototype, okay, so EG with and also because you are Basai student, okay, deliverable would be okay, paper, code, and data. Now, data set can be like you use outside data set. If it's big, you can point to URL. But if it's not that big, you can say you download, you can submit. But I prefer that you point the link, okay? Code and data. And including access. And finally, again, because you are Basai student, video presentation, 5 minutes. You are thinking. Okay? Now, in the paper, you need to do also survey. So let me write that as a separate. This means some this means literature. Okay. Now we'll talk about it later. So the paper will have all the above, right? All the methodology and all the stuff. And so this is going to have, abstract, intro, survey, method, experiment, conclusion, and bibliography, links. Okay. Now, let me show you, for example, this is an assignment I gave to my kid. Okay, so this is an assignment I gave to my kid. Now, when he writes a paper, the code is not in here, obviously, right? So he puts it in like GitHub. So you may do that. Okay, like, or you may point to cloud or something like that, right? So in other words, when I say submit the code, you don't have to sort of like submit into a zip file or something like that. So this would be normal way people do things nowadays. So you write a paper. So this is my kid's assignment, and now analyze COVID data. And this is the same. I suggest that he uses the same thing that I was using as well. But anyway, all the codes are in the GitHub. Likewise, you don't have to have a GitHub. You can put in your cloud or something like that. Okay, so give a link in there. Yeah, so give a link in there. So prefer okay. I don't know, Jula gave you cloud space. I don't know if Jula gave you one. So I think Basai student may have a bit of cloud space given, but you should have enough. Yeah. So likewise, this one you can upload to YouTube first, if you like. Okay, so that's what I want to say. So the thing is, you should by now. Now this thing a little bit you haven't really been able to do. Okay, but this thing I think you should have been thinking about in your homework, right? This thing you should get more and more clear idea. Okay, this thing of course you have to do, and the data. Think of your data set. So bits about your project. Okay, let me give you that. So that's done. Okay. So let me give this to you right now before I forget. Class 8 side notes. Okay, and I'll give you. I'll give you sort of like bits and pieces. Okay, Kap. Other than that, all good. I've covered everything I wanted today. Again, go read. You know, there are a few mathematical functions that we talk about. Take, drop. Okay, take, drop, thread. I like this one. You may not use it. Okay, association. Okay, data set. Go look through those. Okay, and I think I have more links here. Yeah, data set. I might as well give it to you guys. Thanks. Right. Now, okay, and this one, this is just listen away. Never mind. This is a little bit more advanced. This one here, for those of you who are really into like web scraping. Okay, but that's quite fun once you get into it. I'm not into web scraping all that much, but I would imagine your generation likes this kind of thing. Okay, Kap. Other than that, I've covered everything. Sorry, we went a little bit over time, but okay. นะครับ
ครับ
Okay, I think that's it, จ้ะ
โอเคครับ thank you